Why black hole environments are more complicated than we thought. The cosmos far beyond our planet is filled with things so weird and wonderful that it can be difficult to believe they exist. Perhaps the weirdest of them are all black holes, bottomless pits that devour stars, powers the centers of galaxies, and warp space and time. If you get too close, the entirety of time may pass you by and there is no return. We don't yet know all the details of how black holes work, but this is not the same as having no knowledge at all. So let's peer into the darkness and resolve what we can and bust some myths about along the way. Black holes are some of the strangest and most fascinating objects in space. They're extremely dense with such strong gravitational attraction that not even light can escape their grasp. The Milky Way could not contain over 100 million black holes, though detecting these glutinous beasts is very difficult. At the heart of the Milky Way lies a supermassive black hole, Sagittarius A. The colossal structure is about 4 million times the mass of the Sun and lies approximately 26,000 light-years away from Earth. Scientists can't see black holes the way they can see stars and other objects in space. Instead, astronomers must rely on detecting the radiation black holes emit as dust and gas are drawn into the dense creatures. But supermassive black holes lying in the center of a galaxy may become shrouded by the thick dust and gas around them, which can block the telltale emissions. Sometimes as matter is drawn toward a black hole, it ricochets off the event horizon and is hurled outward rather than being tugged into the maw. Bright jets of material traveling at near relativistic speeds are created. Although the black hole remains unseen, these powerful jets can be viewed from great distances. The EHT's image of a black hole in M87, released in 2019, was an extraordinary effort, requiring 2 years of research even after the images were taken. That's because the collaboration of telescopes, which stretches across many observatories worldwide, produces an astounding amount of data that is too large to transfer via the internet. Albert Einstein first predicted the existence of black holes in 1916 with his general theory of relativity. The term black hole was coined many years later in 1967 by American astronomer John Wheeler. After decades of black holes being known only as theoretical objects, the first black hole ever discovered was Cygnus X-1, located within the Milky Way in the constellation of Cygnus, the Swan. Astronomers saw the first signs of the black hole in 1964 when a sounding rocket detected celestial sources of X-rays, according to NASA. In 1971, astronomers determined that the X-rays were coming from a bright blue star orbiting a strange dark object. It was suggested that the detected X-rays were a result of stellar material being stripped away from the bright star and gobbled up by the dark object, an all-consuming black hole. According to the Space Telescope Science Institute, STSCL, approximately 1 out of every 1,000 stars is massive enough to become a black hole. Since the Milky Way contains over 100 billion stars, our home galaxy must harbor some 100 million black holes. Though detecting black holes is a difficult task, and estimates from NASA suggest there could be as many as 10 million to a billion stellar black holes in the Milky Way. The closest black hole to Earth is dubbed the Unicorn and is situated approximately 1,500 light-years away. The nickname has a double meaning. Not only does the black hole candidate reside in the constellation Monoceros, the Unicorn, its incredibly low mass, about 3 times that of the Sun, make it nearly one of a kind. The first image of a black hole was captured in 2019 by the Event Horizon Telescope EHT collaboration. The striking photo of the black hole at the center of the M87 galaxy 55 million light-years away from Earth thrilled scientists around the world. Black holes might be more complex than scientists have thought, according to a new study which suggests for the first time that these mysterious objects might be exerting pressure on their environment. Known for their extremely powerful gravitational force that sucks in everything from their vicinity, black holes were originally believed to be completely inert. In 1974, famous cosmologist Stephen Hawking discovered that these super-dense objects are in fact emitting thermal radiation. A new discovery, made by a team of scientists from the University of Sussex, UK, now hints at an even more complex nature of these massive space drains. Astronomers Xavier Comet and Volker Kuipers concluded that black holes exert pressures as they study the changes in gravitational forces caused by the behavior of quantum particles at the edge of black holes and the entropy or the available energy of that system. Our finding that Schwarzschild black holes, static black holes without electric charge, and angular momentum have a pressure as well as a temperature is even more exciting given that it was a total surprise. Xavier Comet, professor of physics at the University of Sussex and one of the authors of the new study, said in a statement, "I'm delighted that the research that we're undertaking at the University of Sussex into quantum gravity has furthered the scientific community's wider understanding of the nature of black holes. The pressure exerted by the black hole, Carmen said, is rather tiny. Still, its existence might help scientists improve their understanding of the behavior of black holes and how they marry the rather incongruous principles of quantum mechanics, thermodynamics, and gravity. As they ran their calculations over and over again, an extra figure was showing up that they had no explanation for. Eventually, they concluded this unaccounted variable must represent pressure. If you consider black holes within only general relativity, one can show that they have a singularity in their centers where the laws of physics as we know them must break down. Comet said, "It is hoped that when quantum field theory is incorporated into general relativity, we might be able to find a new description of black holes." Fulford Quippers, a doctoral researcher in the School of Mathematical and Physical Science at the University of Sussex, and the second author of the paper, added, "It is exciting to work on a discovery that furthers our understanding of black holes. Our result is a consequence of the cutting-edge research that we are undertaking into quantum physics at the University of Sussex, and it shines a new light on the quantum nature of black holes." The discovery is described in a paper published in the journal Physical Review D on September 10. When a star burns through the last of its fuel, the object may collapse or fall into itself. For smaller stars, those of about 3 times the Sun's mass, the new core will become a neutron star or a white dwarf. But when a larger star collapses, it continues to compress and creates a stellar black hole. Black holes formed by the collapse of individual stars are relatively small but incredibly dense. One of these objects packs more than 3 times the mass of the Sun into the diameter of a city. This leads to a crazy amount of gravitational force pulling on objects around the object. Stellar black holes then consume the dust and gas from their surrounding galaxies, which keeps them growing in size. Supermassive black holes may be the result of hundreds or thousands of tiny black holes that merge. Large gas clouds could also be responsible, collapsing together and rapidly accreting mass. A third option is the collapse of a stellar cluster, a group of stars all falling together. Fourth, supermassive black holes could arise from large clusters of dark matter. This is a substance that we can observe through its gravitational effect on other objects. However, we don't know what dark matter is composed of, because it does not emit light and cannot be directly observed. For all that we've learned, it's either the case that black holes really do exist, or the laws of physics as we know them need to be tweaked. But for us to accept the latter option, those tweaked theories will need to be developed, tested, and proven, and still be able to explain simpler physics like why you don't float away from Earth when you jump, or how we can use gravitational boosts of planets to get spacecraft to specific targets in the outer solar system.